All right, so we were talking today about solutions. Okay, it's our next unit. We've already talked about solutions. We've already talked the fact that solutions are something called mixtures. Okay, so if I just white some of this out here, what is a mixture? Okay, well, a solution is a homogeneous mixture. So if I have NaCl, if I have, let's say, sodium chloride, an ionic compound, and I have a solid, and I dissolve it in some water. It's my time now, people. You've had your opportunity to talk. Now it's my time. Okay, what we're going to get is an NaCl aqueous if it dissolves. And anytime you've got a salt, an ionic compound, or even a molecular compound with an aqueous, it's screaming to us that that has been completely dissolved. A couple of words, we say it's miscible. Now we should know why it would dissolve. Okay, why would something ionic dissolve in water? Well, we know that ionic compounds have a positive and negative end to them. And so does water. Water is an excellent solvent because it is polar. It's got a positive end and a negative end. In fact, we've talked about this already. But what I want you to understand is when I say the word solution, okay, I am screaming to you that there are two things going on. There is a solute. There's a substance being dissolved. In the case of water dissolving or salt, sodium chloride dissolved in water, this is my solute. It's the substance being broken down into its smallest pieces and mixed evenly with the solvent. The solvent is a substance that does the action on the solute to get it dissolved. What does dissolve mean? Dissolve means essentially that the solvent is able to break this compound into its tiny pieces and mix it evenly throughout the mixture. That's why it's a homogeneous mixture. You learn in October a homogeneous mixture is AQ. Well, I'm now changing that and building upon that to tell you that AQ means we have now a solution. Okay? Now we've talked about it. What kind of attractive forces does the water do on this ionic compound to make it dissolve? What is that called? What is that action on the salt? What is it called? The attractive forces. Well, you can read. It says molecule ion. Okay, and I'm having all kinds of difficulties. Let's go back up. So it's a molecule ion attraction. I don't know what they want for that, but that's good enough for me. So here we go. So what we're seeing here is I added a solid. I'm stirring and it disappears. It seems like it disappears. Now the color could change, but what's happening in the crystal, in this case, the negative end of the water is surrounding the positive ion, and the positive end of the water, the H's, are surrounding the negative ion, and that's called the molecule ion attractions. That's hydration. That's dissolving right there. We can't see individual ions. We can see a bunch of these stuck together, but individual ions we can't. So as we dissolve, it looks like the solution is disappearing, the solid, but it's not. It's just becoming so small that our eyes can't pick it up. And that's what dissolving is. But why was water able to do that? Why was water able to do that? Because it had similar attractive forces, and that's very important. The reason why water can dissolve things like ionic compounds. Water has a negative and positive side. Ionic compounds have a negative and positive side. So we learned, this is very important, like dissolves like. So it's very important you understand that. Case in point, okay? What I have here is a chair. Now it's gone. I want a stool, so let me grab a stool. Is there a pigeon on it? Now, here's my stool. I was fighting tigers, I guess. And what I have here are packing peanuts. Okay? Some packing peanuts. These are environmentally friendly packing peanuts. Okay? Now you may have seen these in bio. Now, I also have what the other packing peanuts used to be made up of. There's styrofoam packing peanuts and they're environmental friendly packing peanuts. What's the difference? Well, the styrofoam packing peanuts, the same thing that makes any kind of these hot containers, okay? You put them in water, clearly, there's nothing going to happen here. Okay? The water and the styrofoam do not interact. Therefore, would you say water is polar? Would you say this isn't polar? Is like dissolving like here? No, because this water is polar, so this must be non-polar, which means this has no negative or positive side for water to do this to. So water can't dissolve this, which is a good thing because people would be called what? Holding their what? Coffee, and it'd be spilling in their hands if it did. So we choose plastics or polymers that are non-polar because it doesn't dissolve. Now, packing peanuts have forever been made of styrofoam. The problem with this, it doesn't break down very easily. However, these packing peanuts are made of starch. So these starch packing peanuts, if you don't know what starch is sugar bonded to sugar, and sugar is very what? Polar. Sugar dissolves in water. So if I put these in hot water, okay, these will actually dissolve. Okay, and for lack of a stir, I guess I use a straw, I could take these environmental friendly peanuts, and as I stir, they'll dissolve.
Because they're polar?
Because they're polar. So the environmental friendly, now if you know if you have these because when you put them in your hands, they actually feel sticky. If I was brave, I would eat one for you. But I'm not going to eat one because they've been in this lab forever. But I could pop my mouth and eat them as starch. They're not going to taste like much. It's kind of like eating those wafers, those diet wafers or something. Okay? So clearly they dissolve. And why? Because they're polar and water is polar. Like dissolves like. Now, my friend in chemistry, let's go back to the styrofoam. Can I dissolve that? But what will I need?
Something non-polar.
Something usually non-polar. So I'm going to take a solvent, okay, that's different from water, and I am going to try to dissolve it. Now, of course, here it is, okay, and I'm going to fill it with a solvent that's different, that's non-polar. This is non-polar. Like dissolves what?
That was like, why is it getting shorter?
Like dissolves like.
It's yellow.
It's dissolving the components of the styrofoam. Okay? So if I was to ask you, if I'm making a solution, if something dissolves in something, what are you telling yourself? You're telling yourself, is it polar dissolving polar? Is it non-polar dissolving non-polar? Like dissolves like. Why? Why did the styrofoam peanuts dissolve? Because the polar water, negative or positive, had something to attach itself to. The nonpolar molecule with the LDF forces had something to attract the other LDF forces. It's about the attractive forces you've learned, yes?
Did the water need to be hot?
It made it go faster because temperature affects solubility. Now, the ability to dissolve things is called solubility. The ability to dissolve. Now Sam recognized I used hot water, and I was using a trick. I know that things are hot, they dissolve better. Think with me. Think how this was moving. I want you to visualize this, party people. Okay? I want you to visualize. If the temperature goes up, watch. Here's cold temperature. I'm dissolving, but very slowly. If temperature goes up, whoa! Slow temperature. I just move very slowly. Then fast. Whoa! Okay? As temperature increases, and you increase the motion of your solvent, which was the water in this case, who was the solute? What got dissolved? The starch. Okay? If I increase the temperature, the solubility increases. Okay? Now, interesting enough, party people, some paper can be dissolved also in water. So I got regular paper. Paper must be what? Non-polar. Like dissolves what? Like. That's the same paper that we have here? No, I made some polar paper. I got some polar paper. Okay, now, what about this chart behind me? This chart behind me tells me something about solubility. So let's get this off here. Okay, and this is what today's about. This is a solubility curve chart, so let's talk about it. All right, let's get this stuff back. Now, what are we looking at? We're looking at solubility curves. Now, solubility is the measure of how well a substance does dissolve. Now, as Jordan pointed out, I was using one property of solubility. I'm sorry, Sam, okay? That temperature affects solubility. It is totally intuitive. If I make the solvent, in this case, it's going to be water, okay? Warmer, the ability to dissolve solids, or how much I can dissolve, increases. Here we go, party people. Here's how you work this graph. Let's look at ammonium chloride. Look at this curve. Watch what I say. If I'm at 0 degrees Celsius and I have 100 grams of water, we say that we can dissolve exactly about 28 grams of ammonium chloride in 100 grams of water. On this line is called a saturation point. That means 100 grams of water at 0 can maximally hold in solution 28 grams. Any more than that, okay, once I pass the saturation point, a solid, I'll see that at 0 degrees Celsius, this number here is how many grams of this substance. So there's 28 grams of ammonia chloride that can be dissolved at 0 degrees Celsius in 100 grams of water. This whole chart is based on 100 grams of water. Now watch. As temperature increases to 100, now we would say approximately 77 grams of ammonia chloride can be dissolved in 100 grams of water at 100 degrees Celsius. As temperature increased, what happened to the ability of the water to dissolve the salt? It increased. Now, the words that we have to learn are saturated. If I'm on the line of this curve, it tells me the solution is saturated. So for instance, if I was to go here, if I said I have a saturated solution of ammonia chloride at 70 degrees, at 85 degrees. Let's pretend it's 85. Just find a nice point. If I have a saturated solution of ammonia chloride, I'm on the line. This tells me the maximum amount. How many grams is necessary to make a saturated solution of ammonia chloride at 85 in 100 grams of water? 70. Okay. Now, another factor of solubility is how much solvent you had. Remember those guys tearing up the salt? What if I had more of them? Could you hold more water? Yes. So what if I had the same problem? How many grams of ammonia chloride can be dissolved in 200 grams of water at 85 degrees Celsius? I want to make a saturated solution, that means on the line, for ammonia chloride. I know 70 makes it on the line in 100 grams of water. If I have 200 grams of water, double that. Hey, what if I had 50 grams of water? Half that, right. Okay, now what if I'm here? What if I have 60 grams? Remember, this is the grams of the substance. And 100 grams of water. If I have 60 grams of it, how many grams do I have to add to make it saturated? So I have 60 grams of ammonium chloride at 85. How many grams do I need to add to make it saturated? 10. Okay? So those are the basic ways that we look. Factors are how much water and temperature. All right? So, we'll leave that alone till now. Those are the basics. I have no homework except you're studying for your dog tomorrow.